Okay guys, so sorry that last video just cut off a moment ago, and I didn't quite get to finish up my conclusion here. So just what we basically have proved is that the whole real numbers with the absolute value metric is homeomorphic to the positive real numbers with the same metric. Okay? So we showed that there's a bijection, which was the exponential function, and then we showed that pre-images of open sets are open and images of open sets are open. So these two spaces are homeomorphic. Now that leads me to a follow-up question, which was raised a little bit earlier in the review. And what that is it true that if, let's just say, y and z are homeomorphic subspaces of X. So if we have a topological space and we have two subspaces of that which are homeomorphic to each other, and if Y is dense in X, then is it true that Z is dense in X? Okay, in other words, the question is, if I have a homeomorphism between two spaces, and one of them is dense inside of some big universe space, such as, in this case, the whole real numbers, and the other one is homeomorphic to it, is that one also dense? In other words, is denseness something that is preserved by homeomorphisms? And so this would be a natural question. I mean, we've already, earlier in the review, we saw that T0 is preserved under homeomorphisms. Connectedness is preserved under homeomorphisms. So the question here would just be, is denseness preserved under homeomorphisms? And interestingly enough, we can see that from this example, that the answer is no. Because, for example, X, in this example above, X is dense in itself. Any topological space will be dense within itself. Remember that denseness just means that the closure of the set is the whole space. Okay? But as you can see, so in other words here, the closure of the whole real numbers is the whole real numbers. Okay? So the real numbers are, of course, dense within themselves. And then, in general, remember, let me just remind you of the definition. A is dense in X. That just means that the closure of A is equal to X. Okay, so any space will always be dense within itself because the closure of the whole entire capital X is just capital X, right? That's what this is saying right here. Okay. Now, however, in this case, if we look at the closure of the positive real numbers, right? So this is going to be the intersection of all closed sets that contain this one here. And it's pretty easy to convince yourself that that closure is exactly this closed set right here. Okay, so the closed interval from 0 to infinity, that is going to be the closure of the interval from 0 to infinity, and that is not equal to the whole real numbers. Okay, so in this case, Y is not dense in X. Okay, Y is not dense in X. So just because two spaces are homeomorphic to each other, and one of them is dense within the universal space, doesn't mean that the other one is. Okay, so there's an example of a property that we've talked about that is not preserved by homeomorphisms. Okay? Okay, let's do a couple more examples of homeomorphisms here. Let me give you another set, X and Y, and let's see if these guys are homeomorphic to each other. Suppose that X is the set 1, 2, 3, 4, and tau is the empty set, the set 1, the set 1, 2, and the set 1, 2, 3, and the set 2, and the set 1, 2, 4, and the set 2, 4, and the whole space X. All right, so a big topology there on X, and then I'm going to take another topological space. This is going to be Y, which has 4 elements, A, B, C, and D. And my topology tau prime for this one is going to be the empty set, all of Y, the set ABC, the set BCD, the set BC, the set C, the set B, and the set AB. And the question is, are these homeomorphic or not? Is it possible to construct a bijection between X and Y that preserves open sets, essentially, in both directions? So, I always like to first think about whether there's a bijection at all. And because there's 4 elements here and 4 elements here, it's not surprising that, you know, we might suspect that there is at least a bijection. So I can make a function from X to Y, and because this is such an arbitrary example, you know, we literally are going to define this function by just expressing what is f of 1, f of 2, f of 3, f of 4, and so on. This is what we're actually going to do. Now remember that open sets have to be mapped to open sets. Pre-images of open sets have to be open, right? So we can't just define this bijection however we like. We have to be a little bit more careful, okay? Just to give you an example of the sort of conclusion that you might be wanting to think about, right? Take a look here in the set tau prime. I have singletons C and B. These are singletons, and those are the only 2 singletons in tau prime. The pre-images of those singletons will be singletons because, you know, this is a bijection, so the pre-image of a 1-element set is going to be 1 element. So I know that if these two sets are each open within tau prime, their pre-images will need to be open within tau. And there's only 2 singletons in tau as well, right? So you can, for example, figure out that the 1 and the 2 have to be mapping to the B and the C, right? Just based on that kind of reasoning. Okay? And then it's just a matter of trying to figure out what else we can say. So here's obviously the BC, right? The pre-image of BC is going to have to be 1, 2, right? So that we've kind of got the 1 and the 2 associated with the B and the C. Now, notice that also the B and the C are showing up here and here, okay? But in this case with A, and in this case with B. And notice up here, the 1, 2, 3 is going, and the 1, 2, 4 are showing up. One of them with 3 and one of them with 4. So the 3 and the 4 are going to be corresponding to A and D, right? And it's just a matter of trying to figure out now how this correspondence is going to work. Notice that there is one other set in tau prime of size 2, which is AB, and there's one other set in tau of size 2, which is 2 and 4. That should give us a clue that the B, remember that we said the B and the C are going to be corresponding to the 1 and the 2? Well, the B and the A are corresponding to the 2 and the 4. So that pretty much forces B, if there is such a homeomorphism, B is going to have to be the image of 2, okay? And therefore, C is going to be the image of 1. Okay, so we're going to get C and B like that. And as I was saying, the A the A is going to have to coincide with the 4. So the A has to go here, and then the D would have to go there. This is the only function, based on the analysis I've done so far, the only function that even has a chance of being a homeomorphism. Now, we really should stop and check. You know, maybe somebody just asks you to write down the homeomorphism, then this is fine. But if you're being asked to check it, and you're trying to prove that it works, then you really have to show that it's continuous and that the inverse is continuous. So for instance, I'm going to have to look at the pre-image of every single open set and make sure that it's open, right? So I go along everything here in the codomain, right? So the pre-image of every single one of these open sets. It's going to be a little tedious, but it's not conceptually that difficult. We're just writing down every single open set, and we're going to start calculating in a minute. We're going to start calculating these things. Let's see, I've got to do just a couple more over here. The pre-image of C, the pre-image of B, and the pre-image of AB. Okay, so all of these calculations that we have to do. So you just have to look at the function and figure this out. The pre-image of the empty set is always empty. The pre-image of the whole space Y is always all of X. The pre-image of ABC, which inputs would map to ABC? Well, you can see from here that that's the set 1, 2, and 4, just by looking at your function, right? The pre-image of B, C, and D, well, that's going to be 1, 2, 3. Okay. The pre-image of B and C, well, that's going to be 1 and 2. The pre-image of C is just 1. The pre-image of B is just 2. And the pre-image of A and B is just 2 and 4. And what you should notice is that all of these answers, right, everything that we calculated is a set that is in tau. So that just means that the pre-image of every open set is open. And that means that F is continuous. Okay? If we turn around the inputs and outputs here, we can likewise show that F inverse is also continuous. F inverse is just a function that goes the reverse direction, right? So it's pretty clear at this point that these two spaces are in fact homeomorphic. Okay, so this is a little bit of a different example where you cannot really rely on any intuition from the real number line, right? This is totally a set theoretic based example that really is absent of any Math 350 or any calculus concepts whatsoever. Okay, I want to give you one final example of a question of this nature. I like this one as well, and so I just thought this would be a good time to share it with you. Okay, let me give you 2 more spaces. I'm going to ask you if they're homeomorphic or not. Okay, so the first one, I'm going to call it capital X again, is going to be the set of A, B. I'm sorry, let's just use X and Y. Right. The set of X and Y such that X squared plus Y squared is less than 1. Okay? And this is just a disk. I'll just draw a picture of it here. It's just a disk of radius 1, but without the boundary of the disk. Okay? So it's everything inside of this disk of radius 1, let's say. Now, what do the open sets look like here? We're going to use the subspace topology. So the subspace topology from R squared, that's the whole xy plane, with the Pythagorean metric. So remember that when you use the Pythagorean metric, the open sets are just disks, right? So, and then when you're asking, well, what's the subspace topology? Well, you're just taking those open disks anywhere in the xy plane. You take an open disk and you intersect it with this disk. So for instance, I could take this point right here and take this disk right there. That shaded region is an open set within capital X right here. Okay? But the disk could be somewhere out here even, right? Nothing wrong with this picture here. Let me just move the center over here. Okay? Now, that whole entire disk is open in R squared, but in order to see what it produces within x, I have to do the intersection with x. So it gives me this little sliver, sliver of the disk right there. So that's an open set, right? Just one more example. So we could take, something like this. So here's another disk in R2, right? When I intersect that with x, I get this little region right here. It's a little football shape without the edge of it included. That gives me another open set within capital X. So all of these different shaded regions, they either consist of an entire open disk, or the disk intersected with capital X, which is some of these other kind of football-shaped regions that you kind of see here. Okay, so that's my first topological space. Now, the second one, what is Y? Well, Y is going to be a set of X, Y, Z in R3. We're going to go into R3 this time, such that x squared plus y squared plus z squared is equal to 1, and z is greater than 0. Okay? And this time we're going to use, I'll draw a picture of it in a moment, but I'm just going to write down the subspace topology, right, is going to be from R3, again with the Pythagorean metric. Okay, so again with the Pythagorean metric. Okay, now what is that? Well, let me draw a picture of R3 here. This is the axes for R3, x, y, and z. We're looking at this surface right here. This is just a sphere, right? It's the equation of a sphere of radius 1. And because z is greater than 0, we only want the top half of that sphere. So I guess I could just call this a hemisphere. And we're not even going to include the boundary of where the hemisphere hits the xy plane, because z is supposed to be strictly positive here. Okay, so this is the space Y. It's just this hemisphere. It's just the shell of the sphere. It does not include the inside of it, because this is an equal sign right here. X squared plus y squared equals 1. Okay. So the question is, if we take the top half of a hemisphere and compare it with just a flat disk in the xy plane, are those homeomorphic? Okay. Well, you could kind of imagine somehow pushing crushing the hemisphere straight down into the xy plane, right? You could literally imagine just pushing it straight down, and you'd end up with the whole shell of that hemisphere right into the disk. Notice that the disk that I've drawn right here, this disk, this capital X, is actually just the part of the xy plane directly below the sphere. That actually gives me a great idea for how to at least create a function. Okay, now I'm not going to worry yet about whether it's a homeomorphism, but I can at least create a function where I basically take a point, x, y, z. This would be a point that's, somewhere up here on the hemisphere itself, and I have to somehow find a point that's in the disk below it as an output. Well, the natural thing to think about doing is to think about just simply projecting that point straight down to the point x, comma, y. There's technically a 0 in the z component there, but we don't even need to write that down, because when we look at, oh, you know what, I'm doing this backwards, aren't I? This should be a function from y to x. There we go. Doesn't matter which way you define the function, but I should at least write it correctly. Y consists of the triples, x, y, z. And then when I create the output here, I'm only going to be looking at x and y. Right. Now, one thing that's a little troubling about this function is it might not look one-to-one if you at first glance, because it looks like you can have lots of different values of z, and as long as I keep x and y the same, I keep getting the same output over here, right? It looks like there's lots of different inputs that give me the same output. But that's actually not true. You do not have lots of different inputs here, because remember that z, in order for this point that I'm plugging in to really be on the hemisphere, z does not have a lot of choices. In fact, it has to be 1 minus x squared minus y squared square root. Right? So the square root of 1 minus x squared minus y squared. So there are not many different inputs that give me this point. There's just this one input right here. Okay? And so if you keep that in mind, then it's pretty easy to show that f is 1 to 1, for example. Okay? Let's just do it real quickly. Okay? So let's assume that f of x, y, z is equal to f of a, b, c, for instance. Okay? Well, according to the function, that means that xy would equal ab, which then in turn means that x is equal to a and y is equal to b. Right? So you can start off with that. And then the point now is that, well, z, which is the square root of 1 minus x squared minus y squared, just becomes the square root of 1 minus a squared minus b squared, which is exactly what c is. So, as it turns out, the point xyz is exactly the same point as a, b, and c. Okay. So this is certainly going to be 1 to 1, and it's also going to be onto if I pick a random output over here on the codomain. Let's say I pick xy in the codomain. Well, then our task is to plug something into the function that would give me xy, right? And of course, what you see that you need to do is you've got to have 3 slots here, x and y, right? You want to put the same xy here to get the xy there, and then z, which is the square root of 1 minus x squared minus y squared. So given the x and the y, here's an input that would hit that point x comma y. So this is onto, and it's also 1 to 1. It's a bijection between the hemisphere, the shell of that hemisphere, and the disk in the xy plane. Okay? And again, the open sets over here in x, right, are going to consist of disks or footballs or whatever these different kind of shapes here are. If you take their pre-images, if you take the pre-image of one of these, let me just give myself a little room to draw a better example here. If I take a pre-image of one of these things right here, let's say, right, under this function that we just created, which basically pushes everything down to the xy plane, well, the pre-image is just going to be kind of a, you know, a wobbly open patch along the surface of the hemisphere without the boundary, right? Just the way this disk doesn't include the boundary, its pre-image does not include the boundary either. Okay, and so, you know, pre-images of open sets are going to be open. And similarly, if you start with an open set on the hemisphere and you just push it straight down into the xy plane, it's still going to be open. That's a little bit of a rough explanation. It's not very rigorous. I think it's a little tough to give a rigorous explanation of this particular point. So, but I am just going to make a note that f and its inverse are continuous. And thus, capital X and Y are homeomorphic. They are homeomorphic spaces. Okay? So there you go. We have another nice example of two spaces that are homeomorphic to each other. Okay. hopefully this is making sense. Be sure to ask me if there's anything in these examples that isn't making sense. Of course, you can always go back and rewind and pause and watch this again if you want to. I'm going to do one last example tonight, okay? And then we'll call it good for this review. And this one, excuse me, very easy to state. This is problem number 5, I believe. What I'd like us to try to show here is that every subspace of a regular space is regular. Okay, very easy to state that. Just want to try to show this now. Okay, remember that regular means, just to remind you of the definition, regular just means T1 and T3. Both of those axioms have to be true, or both of those definitions have to hold. And just to remind you about T3, T3 just means that let's just say that capital F is closed in the topological space X, and you take a point X that's not in F, then there exist open sets U and V in the topology such that X is an element of the first open set, I'll call it U. The set F is contained in V, and U intersect V is empty. So that's what T3 means, and I'm putting that, if I put that together with T1, then I get the concept of regular. Okay? So in this problem that we're going to solve over here, I'm going to go ahead and let X tau be regular with subspace. The subspace is going to be W, and then of course the subspace topology is just tau restricted to W. Make sure you are comfortable with what that topology is. It just means that you take sets from tau and intersect them with W, and that gives you the open sets in the subspace topology. Okay? So I'm going to try to show that W is regular. So the first part of that is I'm going to show that W is T1. Now the nice thing about T1 is we had a proposition in class that said that a T1 space can be characterized as a space where all singletons are closed. So what I'm going to do to show that W is T1 is I'm just going to take a singleton and show that it's closed. So let's let W be in that space, capital W, and the claim is that the set W is closed, and let's be very clear here, closed in W. Okay, I already know that singletons are closed in X because X is regular, and so X is T1, but I'm actually trying to show now that this singleton is closed in W. Okay. Now, because the topology is so important to understanding the space, for example, we know what the open sets of W look like. I'm going to, instead of really showing that the singleton is closed here, I'm going to look at the complement of that and show that it's open. So let's consider W minus the singleton little w, right? And, it actually might help to have a picture here. So here's X, and then W is like here, it's a subspace, and here's my little w, right? So I'm taking out that point little w right now, and I'm looking at the rest of W minus little w, which is that shaded region, right? Now, I know that the complement of a singleton in capital X will be open. Now, I'm trying to show that this is open, but I already know that, for example, X minus the set of W, I already know that this is open since X is